So now that we understand how to find all of the various features of a rational function, the vertical asymptotes, horizontal asymptotes, x and y intercepts, um, we're ready to sketch the graphs of some example rational functions. So to keep ourselves on the right track, we'll follow these steps on page 68. One, we'll find asymptotes. Okay. And finding the vertical asymptotes in the domain are sort of one and the same problem. Step 2, we'll find the y-intercept. 3, the x-intercepts. 4, we will find a few extra values, a few more points other than the intercepts that we can plot to sort of ensure that we graph an accurate curve for the rational function. Step 5, we'll put all the information on the xy axis, and then we'll sketch it in our calculator, or plot it in our calculator, and double check our results. Example 1, we have 3x minus 3 divided by x over 2. And so step 1, the vertical asymptotes. In a nutshell, we set the denominator equal to 0, x minus 2 equals 0, so we add 2 to both sides. So located at x equals 2, we have a vertical asymptote. And I'll just do this as I go along. I know one of the steps was to transfer all the information to the graph, but I'll do it a little bit at a time. X equals 2 is our vertical asymptote, and in other words, the domain of f equals negative infinity to 2 union 2 to infinity. What about the horizontal asymptote? We compare the degrees of the numerator and denominator. And the degrees refer to the largest exponent of the polynomial, and they are equal. We have 1 on the top of the numerator, 3x to the first power minus 3, and then the denominator is x minus 2. So we only have one variable and its exponent is 1, so they are equal. That means that we take the ratio of the leading coefficients, and the leading coefficients are 3 and 1. They're the numbers in front of the variables from which we took the degrees, the 1 and the 1 on the bottom. So we would say y equals 3 over 1. And that results in a horizontal dashed line on our graph of f of x. I'll switch back to black, and I will find 1, 2, 3 on the y-axis and draw a dashed horizontal line there. HA, horizontal asymptote, VA, vertical. And now we'll go to step 2, find the intercepts. Y-intercept, set x equal to 0, and then on the bottom if we plug in 0 into our function, we have 0 times 3 minus 3 on the top. And so the x terms just cancel out. We end up with a negative 3 on top, negative 2 on the bottom, 3 over 2. So that is 1.5, 1.5. So we find our y-axis and we go at 1 and then halfway between 1 and 2. Right there. 3, x-intercept, and this one can be a little more involved depending on the polynomial in the numerator. Set numerator equal to 0. If the numerator is 0, then we get 0 for the entire function. So if we have 0 over x minus 2, as long as we don't get 0 on the bottom, then 0 divided by some non-zero number would give us 0 for f of x. So we take the numerator, 3x minus 3 equals 0. Simple equation. It's not quadratic. We simply add 3 to both sides. That leads us to 3x equals 3. And finally, dividing both sides by 3, we get x equal 1. Okay, so this is where our function f crosses the x-axis, and there is x equals 1. So intercepts are actual points that we plot. The vertical and the horizontal, the asymptotes are dashed lines that we locate on our plots. We're not always guaranteed to have a horizontal asymptote. And so our next step, let me see, I can't remember. I'm going to scroll back up to the top. Oh, not too far. Construct a table. So everything's lined up again. And you can tell from the graph that hey, it's great. We got 2 points there in this section, but what about the other sections? We have no idea where the curve travels in this right half here. Is it on the top? Is it on the bottom? So we'll plot some points, and if we want to plot some points over here on this right half, then we need to pick x values that are over here and are greater than 2. So 3, 4, 5, 6, 7, 8, 9, 10, any of those. I will pick this value close to the vertical asymptote, which would be 1, 2, 3, x equals 3. And then I'll space one out over here at x equals 6. So then I'll have two points on the left half, 2 points on the right half. To figure out the y coordinate, I just calculate f of 3 and f of 6. So I take f of x, replace all the x's with 3's. 3 times 3 is 9 minus 3 on the top. 3 minus 2 on the bottom is a 1. So in the end, I just get a 6. And I'll go ahead and plot this point 3, and then I go up to 6, which is just above 5, right about there. Okay, for my next set of coordinates, I want to calculate f of 6. So that would be 3 times 6 minus 3 over 6 minus 2. 3 times 6 is 18 minus 3 on the top. 6 minus 2 on the bottom is a 4. And 18 minus 3 is 15 on the top, divided by 4. And what do we get here? We get 4 goes into 15 3 times and gives us 12. From the 15 I have 3 left over, so 3 3/4, 3.75. So I go to x equals 6, and I go up, let's see, to, there's 3, and I'm pretty close to my horizontal asymptote. The horizontal asymptote is located at 3, so I'm just above it, 0.75 above the horizontal asymptote. So I think I've got plenty of points now. And let's see, what's our next step? So bear with me, I'll make sure I follow the steps the way they're laid out in the workbook. We constructed a table, all the information's on our plot, and so we just want to sketch it. So we're going to come in really close on the far left, close to our vertical asymptote, and as we get to our horizontal asymptote, as we get closer to the vertical one, we start to decline in towards our y-intercept, and now we're just going to drop through our x-intercept and get closer and closer and closer to the vertical asymptote as the function falls. But we never want to cross the vertical asymptote. When we pick it up on the right, we are just to the right of the vertical asymptote on the top. As it falls, it passes through the 2 points that we calculated in our table, and then through that last point we get close to the horizontal asymptote, but we never cross it. And I may have actually touched it, which you don't have to draw these so accurate. This gives me the general idea that you know what you're doing. So at this point, the last step is to simply just verify the graph that we came up with using our calculator. Alright, y equals, and to be on the safe side, the way I'll put it into the calculator is I'll insert parentheses around the top and the bottom. I don't want it to mix my numerator and denominator up, so parentheses 3x minus 3 divided by x minus 2, enter. Graph, and we see, if we count on the x-axis, we have 1, 2, 3 and so it looks just like our vertical asymptote that we plotted here at x equal 2. And then you can see that if we go up 1, 2, 3, let's see, is that 3? our horizontal asymptote at y equals 3 just skims the bottom of the right curve and then skims just above the top of the left curve, and with the calculator it gets really close, but you'll never get a y equals 3 out of this function, and you'll never get a number out of the function if you put in x equals 2. 2 is not in the domain and 3 is not in the range. So we could write out the range. We've already written the domain. Range of f equals all real numbers except 3. So that takes care of little f. We'll clear our screen. Take a look at our next function, g of x. So step 1, the domain of f, or pretty much the same question, where are the vertical asymptotes? What numbers do we not want to put in so that the denominator doesn't become 0? And I'm just used to writing it this way. Denominator equals 0. You could use does not equal if that makes more sense to you. I just know that whatever x's I get from solving this equation, I know that they're not in the domain. So hopefully this is factorable. Always makes it easier to solve a quadratic equation. 1 is our a, so we write x times x is x squared. And then we can say minus 4 and plus 1. 1 times a negative 4, negative 4. Negative 4 plus 1, negative 3. Set each of these factors equal to 0. And we find the locations of our vertical asymptotes. There's 2 this time. So I'll go to x equals 4. Then I'll go to x equals negative 1. And for each location, vertical dashed line. And I'll label them with VA. So these are the vertical asymptotes. That tells us that the domain is negative infinity up to negative 1, and we skip negative 1. We want the numbers in between on the x-axis, so from negative 1 to 4. Skip 4, and then any number past 4 to infinity. So there's our domain. Step 1, we want to find the other asymptote. So we compare the degrees. Degree of the numerator, and the other side we want to do denominator. Degree of numerator, degree of denominator, how are they related? Well, on the top we have a 1 for the numerator, the highest exponent of the polynomial. The polynomial in the denominator, on the bottom of the fraction, highest exponent is 2, and so we have numerator degree less than denominator degree. When this is the case, we say that y equals 0 is the horizontal asymptote. And that falls right on the x-axis. So I just take the x-axis and I put dash marks out to the side of it. If you have a dark pen or a pencil, maybe you can sort of trace along the x-axis. A lot of times I can't see my pencil marks, so I just put the dashes to the side. So on to step 2 and 3, we want to find our intercepts. Alright. Y-intercept g of 0. We plug 0 in for x. We get 4 times 0 minus 8. 0 squared minus 3 times 0. So if you wanted to be quick about it, you could just drop everything except the constants of your polynomial and write negative 8 over negative 4, which is a positive 2. And transferring that to my graph, I put a dot right here on the y-axis at plus 2. And now for my x-intercepts, I simply take the numerator and set it equal to 0. I add 8 to both sides, giving me 4x equals 8. Divide both sides by 4, and I get x equals 2. So that gives me a coordinate right here on the x-axis. And remember, with the horizontal asymptote, we can cross it. Usually cross it somewhere in here, in between or around the vertical asymptotes, but then as you approach negative and positive infinity to the left and right, once it breaks for the far left and right, your function will not cross the horizontal asymptote, but it can in between. So we actually end up with an x-intercept for g of x. So we got a couple points. We sort of have our boundaries here. Vertical asymptotes, horizontal asymptote. But we only have points for the middle portion. What about the left and the right sides? Well, we need to create a table for those values. And if you have your calculator, and this is in the Y editor, real easy to pick some more coordinates to plot this on the test. Okay, plot it by hand. But I want 2 here on the left and 2 on the right. So I'm going to pick some numbers here. Let's see, I'll pick one kind of close on the left of the first vertical asymptote, and that is negative 2. Then I'll pick one a little further away, a negative 5. Now for the right, I want 2 points over here. And so I'll pick 5. And then I guess I'll pick 8. I have no idea what the y's are going to turn out to be. Hopefully some of them work out to be fractions or whole numbers. Okay, so we want to calculate g of negative 2 first. So I have 4 times negative 2 minus 8, On the bottom I have negative 2 squared minus 3 times negative 2 minus 4. This one's a little messy. 4 times negative 2 and then subtract 8 would be negative 16 on the top. On the bottom, the negative and the 2 squared, so that's 4. Negative 3 times negative 2 is plus 6, and then minus 4. So the 4's cancel on the bottom, and I end up with a negative 16 over 6. If I simplify it, let's see, I get 8 over 3. 3 goes into 8 twice. So that would be a negative 2 and 2/3. So when we plot that, we'll do the best that we can. Here's negative 2, and so I go down 2 and almost all the way to 3. We'll plot that point right there. So our next y value is g of negative 5. So on the top I have 4 times negative 5 minus 8. Fill in the x's with negative 5's on the bottom. I get negative 28 on the top. I get 25 from the negative 5 squared, a plus 15, and a minus 4. Alright, on the bottom, let's see, 25 and 15 would give me 40, and then I subtract 4, that'd be 36. 28 over 36 will simplify. Both are divisible by 4. And we get a little less than 1. So it's really close to the x-axis. And so this is negative 7 over 9. And that's going to fall right about there, right on top of the 5. So we have 2 on the left. Now we'll plot these two for the right. But again, we have to find the y coordinates first. Now if I plug in a positive 5, I have 5 times 4 minus 8. So this is quite a bit of work, but it's given us more points to guide our curve. Just walking through the different features of x-intercepts, y-intercepts, those only gave us 2 points. So we want more, need a little help. On the bottom we have 5 squared minus 3 times 5 minus 4. 20 minus 8, 25 minus 15 minus 4, 20 minus 8 on the top is a 12, 25 minus 15 is 10, and then take away 4 more, we get 6, and we actually get a whole number, 2. So at 5 we have 1, 2. Just double checking. 15 minus 4. That is 10 minus 4 is 6. Yep. Okay. My last x value, G8. I've got 4 times 8 minus 8 over 8 squared minus 3 times 8 minus 4. 4 times 8 is 32 minus 8, 24. 8 squared is 64 minus 24 minus another 4. So that becomes 40 minus 4 on the bottom. 24 over 36. And let's see. 4 divides into both. 6 over 9. And then that becomes 2 over 3. So 2/3. So I find x equal 8, 6, 7, 8, and I go up 2/3. Now I'm ready to graph my curve. Start out on the far left, and our points are below the horizontal asymptote. So I want to start really close, just below the horizontal asymptote. Stay pretty close to it, and then once I get closer to my points, break downward and pass through my 2 points, and then drop off really steep before I actually hit my vertical asymptote. Now inside the 2 vertical asymptotes, I'll start on the top just to the right of the first vertical asymptote, stay pretty close to it, and once I get close to my y-intercept, break to the right, pass through the 2 intercepts, draw my curve right up close to the second vertical asymptote. So that completes the center, and then I'll pick it back up. Since this first one is above the one to the right, I'll start way up here again on the top, just to the right of the second vertical asymptote, and I'll trace alongside of it, passing through the 2 points, and then getting closer and closer to the horizontal asymptote and trying not to touch it. Just draw it really close to the x-axis. And so I'm happy with this. I'll go and check my calculator now. I'm not sure if I calculated all these y coordinates correctly. We'll find out here in a second. I'll clear the last one out, and I'll make sure to put the numerator and denominator in parentheses so they don't get mixed up. Minus 3x minus 4, close parentheses, enter, graph. So we come in from the left, below the x-axis, and then it drops down. My first vertical asymptote here at x equal -1. Then we have the centerpiece, which matches up with what I drew in between the vertical asymptotes. I'll trace that in red. So that looks pretty accurate. And then we have the far right curve, and I drew it just like the calculator. Drops in from the top on the right of the vertical asymptote and then falls through those 2 points and levels out just above the x-axis. But what I want to do is go to my table and see if I've calculated these numbers right. So second table, and I put in, let's see, -2. I'll scroll up my calculator my table, -2 and -2.667, which is 2/3. So that was right. What about x equals -5? -7/9, 0.7778. I'm not sure about that one, but it's probably close. And then I'll check my other two numbers, 5 and 8. 5 gave me 2, which is what I had, and 8 gave me 0.666666, which is 2/3. And so I'll go back up here and check my 7/9. Second quit. 7 divided by 9 is repeating decimal, 0.7. And so that completes the graph of g of x. Last function h that we'll graph in this section, 3x squared plus 6, x squared minus 2x minus 3. What's the domain? Or in other words, where are the vertical asymptotes? Where? Simple as far as what you need to do, but actually solving this equation can sometimes be a little difficult. Take the denominator, set it equal to 0. We can factor this one. X minus 3, x plus 1. That gives us -1 and 3. So let's see, I'll draw my vertical dashed lines at these x coordinates. X equals 3 would be here. Not so vertical, but I think you can understand. The next asymptote, horizontal, we compare the degrees. The degree of the numerator is 3x squared plus 6, so the degree would be 2. What about the denominator? It would also be 2, and so they are equal. That means we need to go with the ratio of the leading coefficient. So where is the horizontal asymptote located on the y-axis? Well, it would be y, lead coefficient of the numerator divided by the lead coefficient of the denominator. Real easy to find those. Where did you find the 2 on the top for the degree and the 2 on the bottom for the degree? And then take that particular term and extract the coefficient. So on the top we have leading coefficient of 3, on the bottom 1. So y equals 3 divided by 1, or 3. So on our graph we can go to y equal 3 and draw a dashed horizontal line. So horizontal asymptote and vertical asymptote. Again, we have 2 of them. The domain would just be all real numbers, skipping these two that we found for the vertical asymptotes. -1, skip -1, 2, 3, and then pick it back up with 3 on out to positive infinity. So there's our domain. Step 2, y-intercepts. We want to calculate h of 0, and so we just need to pick up these numbers here. 6 over -3, -2, and so that gives us 1, 2, that point. 3, x-intercept. We have 3x squared plus 6 equals 0. You set the numerator equal to 0. Subtract 6 from both sides. Divide by 3. X squared equals -2. Now we take the square root of both sides, and we have x equals plus or minus, let's see, I square root of 2. So in other words, we don't have any real x-intercepts. We don't actually touch or cross the x-axis. So unfortunately, we only have one point plotted here. We'll have to plot more points with our table. So 4. I am going to cheat this time, and I'm going to use my calculator to put in, to find some points on the graph of this curve. Let's see, we go to the y-editor, clear, parentheses around the numerator and parentheses around the denominator. X squared on the bottom minus 2x, and then we have a minus 3 enter. And I'm going to go to the table. I want some values over here on the left, some more in the middle, and then some on the right. So I'll pick, let's see, -3, -6. These are my points on the left. Another one in the middle, so that would be 1 right here, and then I'll do 2 since I'm using my calculator, and then a couple over here on the right side. So I'll do 4, and then I'll do 6. So using the table from the calculator, it's already done all the work for us. -3, we have 2.75. -6 is a 2.5 approximately. 1. Okay, we need to scroll down to the positive values of x. 1, we have -2.25. 2, we have -6. 4, 10.8. We just about went off our graph there. 6 is 6.75. So here we are on the x-axis, 1, 2, 3, and we want to go to 2.75. So almost touching the horizontal asymptote. Well, -6, we have, let's see, 2.5, so a bit below this one. And if you look at this, it's getting closer to the horizontal asymptote in here, so I'm thinking it crosses up through there. So I'll do one more point in here close to this vertical asymptote. I'll do 2, -2. So we have 3 times -2 squared plus 6 over -2 squared minus 2 times -2 minus 3. Okay, this is what is the y coordinate at x equal -2. Because I know we can't cross the x-axis. We had these x-intercepts, or zeros I should say, that were complex, so we don't have any x-intercepts. So what does this number work out to be? 3 times 4 plus 6 over 4 plus 4 minus 3. 8 minus 3 on the bottom is 5. 3 times 4 is 12 plus 6, 18. And so we get 3 3/5. We go up, we cross the horizontal asymptote. So 3 and almost 4 lands right there. So this is sort of different. We come in here, we pass through these points, and we shoot up through the horizontal asymptote right there. Right. For my points on the inside, I have 2 and -6. And then at 4, wait, let's see, 2, okay, 2 was -6, I'm sorry. 2 goes here. And 1 is -2.25. So a little bit below 2. At 4, right here beside the vertical asymptote on the right, I go to 10.8. So I'm way up at the top of my graph. Just past 10, right about there. Well, I need to scoot it over a little bit more so that it's just above the 4 right there. One more point, 6, and I get 6.75, which is right there. Alright, I know I don't cross the x-intercept, so in between the two vertical asymptotes I'm going to shoot up really close to the right, pass through these 3 points, and swoop back down, avoiding the x-axis. And then on the right side of this inner part, I get really close to the other vertical asymptote as I drop to -infinity. And now on the right side, I come in from the top, pass through these 2 points, and I fall and gradually get closer, and I slow my descent as I get closer to the horizontal asymptote. So let us see what the calculator Here's my calculator, there's my Y editor, and I have my function already input into the Y editor so that I could come up with some values on my table. I graph it, and it looks pretty much the same. And if I go to y equal 3, 1, 2, 3, I can see that the calculator sort of shows that I crossed the horizontal asymptote on the left, just like my graph does. And this part in the middle is sort of skewed. And then we don't come in as steep on the right as we did on the left. So this is a little less symmetric than what we're used to. Alright, so that completes C, or yeah, h of x. And we wrap up this section with an application problem. It reads, for a person with sensitive skin, the amount of time the person can be exposed to the sun with minimal burning can be modeled by T equals 0.37 S plus 23.8 divided by S, where S is the Sunser scale reading. It's based on the level of intensity of UVB rays. Find the amount of time a person with sensitive skin can be exposed to the sun with minimal burning when S equals 10 and S equals 100. Well, all we have to do is plug in these values. 0.37 times 10 plus 23.8 divided by 10. And this is going to give us the time in hours. Okay, in hours. So 10 times 0.37 is 3.7 over 10. We add these two, we get, let's see, 0.5 and then 7, so 27.5 over 10, and divided by 10 simply moves the decimal place to the left once, and I get 2.75 hours. What about S equal 100? Hundred times 0.37 is 37. Alright, since we have 100 for S on top, we put the 100 on the bottom. 37 plus 23 is 40, 60.8 over 100. And divide that by 100, it moves the decimal point to the left 2 places for 0.608. So less than an hour. Okay. So really nothing to that. Just plug in the 10 and plug in the 100 and evaluate each one. 2. If this model is valid for all S greater than 0, what would the horizontal asymptote of this function represent? Okay. Horizontal asymptote, to figure that out, we simply say we compare the degrees of the numerator with the degree of the denominator. Alright, and we have 1 on the top, 0.37 s to the first power, so 1. And then we only have an s on the bottom, so the degree of the denominator is also 1. They're equal. So we use the ratio of the leading coefficients when they're equal, and we have a horizontal asymptote of 0.37 over 1, which is just 0.37. So in other words, as S gets very large, okay, that tells us that the amount of time that we can stay out in the sun with minimal burning is 0.37 hours. Okay, so for instance, if we were to calculate the time for minimal burning of, let's say, 1,000 versus I don't know, 10,000 sensor scale or sensor scale. I've never heard of this scale, but 1,000 versus 10,000, it's probably not gonna vary much as we get out closer and farther to the right on the scale. So the difference in time is probably not going to be much. So t in either case is going to be approximately 0.37. Alright, so past a certain amount of time, or past a certain sensor scale, you're really only safe staying out in the sun with minimal burning less than about, you could say, a third of an hour.